The Leather Recycling Project by Eric Chow, Justin Noel, Robert Leathers, and Curtis Garrett III, and advised by Professor Mariam Shafahi. The goal of our project is to demonstrate that used leather can meet or exceed the same quality control standards as brand new leather, therefore proving that leather can be recycled and incorporated into new goods. Throughout our presentation, we will be illustrating the importance of recycling leather, the current leather disposal methods, the tannery process and waste associated with it, our project, its current progress, and our future goals. So first, why is leather recycling important? Both the process of making leather and its disposal have detrimental effects to the environment. The process of producing leather contributes to carbon emissions through air pollution, produces tons of toxic wastewater and chemicals, and consumes enormous amounts of energy and water to produce a small amount of leather. Additionally, once the leather is created, there is no proper disposal method, and most leather products end up in landfills where they continue to pollute the environment. Due to the chemicals used in its production, leather cannot be incinerated and has to be stored separately in a landfill, or there will be a risk of chemical pollution to the landfill and its surrounding environment. With an inefficient creation process and no proper disposal method, the only option left to reduce leather pollution is through recycling. Currently, the only method to dispose of leather goods are through incineration and landfilling. However, neither of these are true disposal methods since leather still pollutes the environment when both are used. In landfills, leather can take up to 100 years to naturally decompose, during which it leaches out toxic chemicals to the surrounding environment. On the other hand, incineration releases toxic gases such as chromium trioxide, which adds to the carbon emissions produced by landfills.
The tannery processes start when the raw hides are taken from the slaughterhouse and transported to the beam house, where the hides are cured in salt to remove moisture and prevent spoiling, then trimmed to remove imperfections, soaked to remove salts, and prepare for the lime bath, which loosens the hair and cleans the hide. After liming, the hair is removed and then relimed before the fleshing process, which removes flesh still adhered to the hide. The next step is to delime the hide by pickling in an acidic solution. After pickling, the hides are tanned in a chrome solution for up to a day. After tanning, alkali are added to the solution to increase reactivity of the chrome, and the hides are then conditioned to specification. After tanning, the hides are dried, sammied, split, shaved, neutralized, fat liquored, and dyed. Once the desired color is achieved, the new leather is conditioned, buffed, and trimmed according to the desired application. This table displays the waste generated from the processing of an initial 2,000 kilograms of raw hide, and breaks down the average amount of raw hide lost in each tanning process, as well as the range of the amount of water consumed. Water consumption varies based on type of tannin used and the type of leather being tanned. This results in a typical amount of 400 kilograms of raw hide being lost in the pre-tanning stage, around 226 kilograms of raw hide being lost in the tanning and post-tanning stage, and finally 11 kilograms of leather or rawhide being lost in the finishing stage, resulting in a total amount of 637 kilograms out of 2,000 kilograms, or roughly 32% of the initial rawhide being wasted, and a typical range of water consumption being between 12,000 and 40,000 liters of water consumed for every 2,000 kilograms of rawhide.
For the Leather Recycling Project, our team was tasked with researching the current state of the leather industry, including the current production methods in place and the pollution generated throughout the life cycle of leather goods. We were also tasked with creating a material testing laboratory specifically designed to test the material properties of new and used leather samples to meet our project goal of proving used leather can be reused and recycled. Machines that our team is currently testing includes the following.
The thickness machine is a simple and effective method to test the thickness of leather test samples. It is required in most tests which measure the physical properties of leather test samples, The base is 3D printed plastic, and the presser foot is attached to a dial micrometer and supports a dead mass which applies a constant force over the area of the anvil and presser foot to deliver a constant pressure to the sample for each measurement taken. In order to take measurements, the presser foot is lifted by the handle at the top of the dial micrometer and slowly lowered on top of the leather sample. The dial micrometer must be zeroed between each sample. The tensile test machine is still in development, but will be used to accurately measure the tensile strength of leather samples and have modifications which would allow the burst strength test to be performed as well. Two-step motors are powered to turn screws which move a horizontal crossbar. Clamps are used to secure the samples in place, and a load cell is used to measure the applied forces. The design is meant to be low cost and affordable, and the exterior structure will be made out of wood to reduce those costs.
The leather conditioner standardizes the relative humidity and temperature of leather test specimens prior to testing. Standardization allows for repeatability among results because the temperature and relative humidity affect many physical properties of leather. Standardization also allows for reliable comparisons to be made between different leather products. This table shows leather conditioning data taken over the course of 24 hours to standardize the material properties for leather test specimens prior to testing in the crack resistance machine. The crack resistance machine determines the resistance of leather to cracking when it is folded or bent around a mandrel. Leather items tested in the crack resistance machine typically includes purses, handbags, belts, and other garments. This test method is useful for manufacturing control in the tannery, specification, acceptance, and quality control in the end product manufacturing plant. This table shows data collected for 9 samples, both brand new and used, using the crack resistance machine along 5 different cross-sections to test for the presence of cracks by inspection on a crack or no crack basis.
This is our rub fastness tester, which is used to test collar fastness, the ability of both the collar and the finish to stay on the surface of the leather. The silver cylinders you see are 500-gram weights with a little piece of felt on the bottom. These come into contact with the leather sample, which sits on the base, the orange piece, and oscillates back and forth to achieve the rubbing motion. The results are determined using a grayscale tester to compare the color before and after testing, with high values indicating high color fastness and low values equating to lower color fastness. So if we move to the next slide, this is an example of a test done on a scrap piece of new leather, tested to 10,000 cycles. There's a noticeable but not huge color change, although the leather has bunched up where the felt was interacting with it. On the right is the actual gray scale, and you can see that as the values decrease, the difference between the two grays increases. This particular test would score at around 3.5 or 4 to illustrate how the results are interpreted.
The flexometer quality control machine is responsible for determining a material's resistance to flexing fatigue by examining how it responds to continuous wrinkling. During testing, cracks will appear on the leather surface. Depending on the severity of the cracks in the leather, we can determine the leather's resistance and predict its life expectancy. The image in the top right displays the type of cracks that appear on the leather surface during testing.
The next steps for this project are to continue with research and data acquisition. This will be done by continuing to work with and improve the machines we currently have, as well as constructing new machines and test apparatus to expand on our materials testing laboratory. As an example, some of the machines we currently have in progress include an apparatus for testing torsional stiffness, a machine for testing tensile and bursting strength, an apparatus for measuring pH levels, as well as a machine that tests permeability to water vapor.